Thank you very much for inviting me. I apologize for not speaking Korean, but if I did, I'm sure you wouldn't understand me. I'm going to show a lot of slides, and I'll go through them quickly. But I've provided hard copy, and I don't intend, if I go through it at a pace where I can explain each slide in detail, I wouldn't get through them. And I'd like to show you the depth and the range and the number of things that we have done. So let's get on with it. You know about nuclear waste. The remarkable thing about it is that there's so little of it. It's very compact. The drilling industry was mostly unaware of this, so they never proposed putting nuclear waste in drill holes. The nuclear industry was not really aware of the capability of the drill holes. But looking at these numbers, 50 years, look at this down here, 50 years, gigawatt years of waste will fit end to end if you simply take the canisters. Will fit end to end in 17.5 kilometers. That's not very long. That could fit in 6 to 12 boreholes, and I'll show you how. It fits even more compactly if instead of using the fuel assemblies, you use the fuel rods. But it can be done without repackaging. This is repackaging. You take these things out, put them closer together. We've looked at everything here, including the criticality issues. They are not an issue. Heating is not an issue. We've studied all of these, all these factors, and in our published papers, we discuss a large number of them. These are the horizontal wells drilled in the United States. These are just some of them. There are over 63,000 wells like this already drilled. If you look at these, each drill hole is indicated by a small dot, and then the horizontal section extends like this. And in this case, they're 3 kilometers long. And this is North Dakota. It's here in the United States. And you can see this is where we get this is the fracking drilling, which is done to extract natural gas and oil. But you drill the hole, the horizontal hole, and then you frack it afterwards to extract the oil and the gas. We don't frack. We are not fracking. We are simply drilling the hole. The drilling the hole is a very gentle thing. It doesn't disturb, doesn't cause earthquakes. This is an important distinction. And it creates a space down here to put the nuclear waste, because the nuclear waste is so compact. The key to the method we're talking about is what's called directional drilling. And this is now perfected. And it doesn't cost more than drilling straight holes. In fact, it costs less holes. So if you're going to drill a hole straight down, it'll cost more than if you go around a bend. And the reason is, when you go straight down, you're going into more compressed rock, and it's harder to drill, and it's slower, and you go through many more layers. And all these things increase the cost. But if you bend it slowly, and that's easy to do, as you saw, 63,000 sites in the United States and Canada, bend it slowly, you can get lots of space here. The sites I showed you there were 3 kilometers long. So it's all the volume you need. I'm going to show you a little simulation here of what we did. So here we have a typical sedimentary rock layout. It works also for crystalline basement rock. It doesn't have to be sedimentary. But what we do is drill a hole down through the water table. So this is a surface drill hole. You then put cement down there, and you cement it in. So the cement goes down, and it goes up the sides. And this protects the drill pipe from the water. It actually protects the water from the drill pipe. So this surface casing with cementing isolates you from the aquifer. We want to be below, far below any aquifers. So you begin with this process. Then, once you've done that, you drill deeper. And we drill down typically 1.5 kilometers. We could go more if necessary. In many cases, we could go less. This puts 1 billion tons of rock above our hole. And this is what's called the kickoff point. At the kickoff point, we begin to curve. It's a very gradual curve. When the fuel assembly goes down this very gradual curve, it's not bent at all because the curve is so gradual. Here we're going into a shale layer. That's ideal. We don't need a shale layer, but a shale layer has a very low permeability, and that's ideal. And then we can go several kilometers horizontally. You pull out the drill hole, the pipe. You put down casing. This is the canister which holds we put the fuel assembly in these canisters. We attach a tractor to it and other aspects. We're using standard technology. We're not inventing new technology here. We are adapting it to the situation. Here you see the assembly in its canister with shielding around it. So it can be handled above the surface with this shielding. It is transported over to the drill site, placed here in this shielding so that it's safe above the surface. And then you lower it into the hole horizontally. You see there's no bending at all. The bending is very, very mild. And you place it, these are the tractors. So these wheels come out and they spin and they push it. We can push it up, we can push it down, we can push it in many different directions. There are many ways to push this thing into a hole. The oil industry has a large number of ways of doing this. There's something called coiled tubing. There's drill pipe. But this is a wireline and tractor. So we push it in until it gets to the end. And then release it. Come back with a second one, and a third, and a fourth, and so on, and line them up in this way. And 6 to 12 of these boreholes will either be a storage place for nuclear waste, because we can retrieve it. It can come back up. You can retrieve it for 5 years, 10 years, maybe even 100 years. And that way it could be used for storage. And we argue that using this for storage, because it is so secure, is a better way of storing the fuel than putting it in canisters above ground. But let's go ahead. And there it is. And you can see all the waste down there, deep underground. And well, this you all know. So these are the kind of these. So this is what we are doing. We haven't yet done it with any nuclear waste. Okay. It can be used for storage or disposal. If you are storing it above ground, that's cheaper than putting it in a borehole. But only for, we estimate, about 12 years. We've looked at the cost of storing it above ground, and the guarding of it, having the security aspects once above ground, are much more expensive than if it's below ground. And as a result, we calculate that after about 12 years of if you're going to store it more than 12 years, then putting it underground in a borehole is actually less expensive. But perhaps more importantly, if you're going to store it underground, and I don't know why you would, there are reasons why people would like to store rather than dispose immediately. But if you store it underground and then you later decide you don't want to use this waste for anything, you'd like to dispose it, all you have to do is fill up the hole. It's disposal ready. So let me talk about safety. And again, this is for sedimentary rock, but I'm going to be showing you, we also have done all the work for crystalline basement rock. With 6 so far peer-reviewed articles, these go into great depth, not to make a pun, but they discuss the safety issues very carefully. And we've done, I believe, some excellent work on the safety of the fuel. I'll show you, I'll give you highlights of that. But you can look at these papers, they're available online. It's open publication, so you can read them without having to pay a fee. And they go into some detail on, which I'll show you slides from these. Siting. Where can you do this? Well, these are the requirements for a site. First one, of course, is you have to have stakeholder consent, informed consent. And that's not a scientific issue, so I won't talk about that anymore today, other than to say this is a issue which my company, Deep Isolation, has worked on in detail. We have some of the world's experts on informed consent working with us. And so we realize that this is the first thing, and it's extremely important, and it's been done terribly by the U.S. government. Everybody knows that, so I can say that out loud. And I can go into details on that, but it's been done terribly. But these are the criteria. Obviously, you have to have a durable hole. You want to have a low permeability formation. You want the rock to be saturated with brine. You want that brine ideally to be stratified. You want it to be a reducing environment, not an oxygenated environment. You don't want a freshwater human exploitable aquifer that comes close to the region. And I'll talk about subluminal shore isolation. So how many sites does this rule out? In the United States, it rules out almost none. Notice there's no requirement for being in an earthquake-free area. And that's very important. And I'll talk more about earthquakes in just a moment. But if you have nuclear waste, it's a lot safer if it's underground than if it's in an earthquake. Earthquakes shaking are at most, the most severe earthquakes are 1 or 2 G. And these canisters are designed to be dropped, and when they're dropped, they'll take 50 G. So the mild shaking is no real problem. What if the canister is broken by an earthquake? I'll show you that breaking of the canister is also not a problem. So earthquake, an important part of our approach is that it works just as well in earthquake-prone country as it does in areas that have no earthquakes. A thing that we can do is because you can have disposal at so many sites, you don't have to go searching all over your country for one really good site where you put all of your waste. You could put your waste at each site where it is now. And I'll show you in a moment that in the stakeholder engagement, the local population prefers to have the waste buried underground at the reactor where it is now. That's a surprise. At least in the United States this was the case. I don't know if it'll be true in Korea, but they strongly preferred, by an 82% margin, that the waste, which is currently stored above the ground, could be put underground. It doesn't have to be reprocessed. It doesn't have to be vitrified. and we could just take the fuel assemblies, put them in canisters, and put them in these holes. You could have a centralized facility. And this is a design for a centralized facility in which we have enough boreholes to cover a large number of reactors. So they don't have, they can be fairly close together, and they can be put together in a single facility if you want to transport all of your nuclear waste to a centralized facility. We have discovered, to our surprise, to everybody else's surprise, that in the United States, the local population doesn't want the waste transported. They would prefer it to be buried down 1.5 kilometers. That's a surprise, and I think it's a very important insight. Well, this is the survey that we did. Again, I don't have time to go through this in detail, but it's available on our website, and you'll have this chart. But what we found is, given several options, would you rather it be transported away to a centralized facility, or would you rather be buried right where it is? The answer was that 82%, and this is in Alabama, Arkansas, Arizona, California. These are 23 different states in the United States. Every state that has a nuclear reactor in it has nuclear waste. And we did a survey in every state. We asked the population, would you rather have it transported out of your state, or would you rather have it buried where it is and keep it in your state? Most people think they would say, not in my backyard, but that turns out not to be true. They are so afraid of transportation that they want it to be buried where it is. Now, I'm not afraid of transportation. And I could argue with them that, no, there's no need to be worried about transportation. But if we just look at what they're thinking and what they're saying and what they want, it's amazing to realize they, right now, would be happier burying it where it is than transporting it out of the state. Here's a video that is available online here that shows us meeting with the local people where we did a test. And by using the thoughtful stakeholder engagement, where you begin by going to the community and asking them, are they concerned about the local nuclear waste? What would you like people to do with it? You listen to them and you talk to them. Of course, in Korea, we would have you do that, not us. But you listen and you talk to them for what they want. Are they happy leaving it where it is for another 10, 20, 50 years so that their grandchildren can take care of it? Or do they want to do something in the next decade? We found in university they want to do something in the next decade. What can we do? We can transport it away. You listen to them, and in the end they say, we like your solution. You're happy for you to do a test where we are. And if you watch the video link here, you will see them saying, we're so happy to have you here. Now, the Department of Energy never achieved that. The nuclear industry never achieved that. Here's the group of people. We had everybody from a local government to high school teachers and students coming. And stakeholder engagement is an art. It's almost a science. It can be done, but you don't do it by going to a community and saying, here's what we want to do. Let's convince you that it is the best way to do it. That doesn't work. So before you do any stakeholder engagement, please talk to us. This is the team we had at the test. So we used a small canister. You can see it here. Had no radioactive material in it. That's why we didn't hold it. But it weighed as much as a canister. It was the right size for the most radioactive source in the United States, which is cesium and strontium. This has been reprocessed from waste, and the cesium and strontium, because they each have half-lives of about 30 years, is highly radioactive. And we did a test showing that we can put this down the hole, we can place it, we can release it, leave it down there, go back, reattach, and pull it back up. So it's retrievable. And this is what the nuclear industry found so amazing. They thought this was impossible. But if they had just called up the drilling industry would say, no, that's not even hard. We do that all the time. So this demonstration had a big impact, made us very well known, not just in the United States. So there's something we call strong isolation. And this is a new concept that we would like to employ at any site that we go to. If we have a site, maybe a nuclear reactor, maybe not, and we would like to place nuclear waste there, we can go down with a pilot hole, small, inexpensive hole, sample the water and the rock. Now, there is a technology that has been developed in which you measure the helium that's there, and you look at the uranium and thorium, and you ask, that uranium and thorium has been there for billions of years, how much helium is there? Because when uranium and thorium decays, it gives off an alpha particle that turns into helium. And from that measurement, how much helium has accumulated, you get a measurement of how retentive this location is. And you can find, as it has been found in locations around the world, some of them show retentivity of over 1 million years. And so if we can determine that the place we're putting the waste holds helium for 1 or 10 or 100 million years, certainly it will hold other isotopes. But it also turns out there are other natural isotopes there. Neon 21, chlorine 36, iodine 129, they're all down there. They're produced by various mechanisms. The chlorine by neutrons being absorbed on chlorine 35. The iodine is a fission fragment. So these are naturally down there. And once again, you can ask, have these moved? Are they where they were? Have they accumulated for, let's say, 1 million years? If they have been accumulating for 1 million years, then that says that the processes of diffusion and advection that are the dangers, because they can carry the waste upward to the surface. But if these things have been there for 1 million years, then the site is demonstrably safe. Yes, you can do calculations. Yes, you can do simulations. But this is an experimental measurement. So we call this strong isolation, and it's the most compelling argument that you can make to the public. Well, this is just more on strong isolation, showing some of the measurements. We didn't do these, but they have been done. It's a well-developed art. You look at the concentration versus depth. You see if that concentration versus depth matches the producing concentration. This iodine 129, it's coming from fission fragments from uranium and thorium. So if it matches the pattern of uranium and thorium, you can then calculate how long it has been down there. And we think this gives a confidence that going down a mile down, 1.5 kilometers, is really the safest place you can put along with nuclear waste. Hey, you know this. Here is the waste. Here's the decay of the waste. Let me just point out that the heating underground comes from the fission fragments, mostly cesium and strontium in the beginning. Then comes the plutonium and other actinides that the public worries about and politicians worry about, but quite frankly is not an issue because it's very low solubility in water, particularly if you require it to be a reducing environment. Unlike a mined repository, we do not fill our repository with air. It's filled with water. The water comes from the surface, but it also comes from water within the rock. Rock is typically a few percent water. It's saline water. Saline water stops the chain reaction. It quenches the reactivity. And so there's no danger of, if there's any danger of a reactivity accident, it's when the fuel is above the ground. Once it gets underground, it's in a quenching environment. And these actinides are not really a safety issue because they're not very mobile. Ironically, the real safety issues are the chlorine-36 and iodine-129, magnesium, and selenium, which are at much lower levels, which are still around after 1 million years. And at least in the United States, we are required to show safety for 1 million years. So we do what we think are the best simulations that have ever been done for underground waste disposal. This is our model. We have 100,000 grid points. This is the model for a horizontal well. This is the model, the digitization for the vertical well in granite and other crystalline basement rock. And these, I'm really proud of these. They were done for us by Stefan Finsterli, who is a world expert in this. He has been the developer of the Tough 2 code, and he has been doing all of this work for us. And these are some of the results. So for the cesium and strontium, the heating reaches its maximum after 10 years, and it goes up from the base level by about 70 degrees Celsius. That sounds like a lot, but it is far from boiling because we are at hydrostatic pressure. We're not filled with air, we're filled with water. And if you look at the boiling point at that depth, it's 300 degrees Kelvin. For spent nuclear fuel, there's heating in the beginning, and then if you have a series of canisters together, as the heat diffuses and spreads out, you get a second pulse. But again, the heating here is about 60 degrees above the ambient. It gets up to almost 100, let's say it passes 100, but the boiling point of water at that depth is not 100, it's way up here. So we don't have any boiling problem, as people do in mine repositories. Let me get to my next slide here. Okay, so these are the sort of simulations that we do. And these are presented in color, but typically we will have a horizontal or vertical repository. We will plot the radionuclides as a function of time, taking into account diffusion and advection. Advection usually dominates. We have a well here, a water well, because we put an aquifer at the top. And we calculate how much of this radioactive material gets into that water well. We assume that there's someone getting all of his water from the water well, 100% of his water from the water well, and then ask what the dose will be, taking into account the iodine-129, which is usually the dominant dose at the surface. So we do these exquisite calculations. Here we look at chlorine-36, and here it is at 100,000 years, and after 1 million years, 1.5 million years, a lot of it is decayed away. Some has gotten up into the surface, but most of it has decayed away because it only has a 300,000-year half-life. Selenium-79, likewise, has mostly gone away. Technetium-99 doesn't go very far because it's insoluble. And iodine-129 is the most important one. It has a half-life of 16 million years. So as we look at it at 50,000 years, 500,000 years, 1 million years, 1.5 million years, and then finally at 100 million years, when it's decaying away, it is feeding this little water well and giving doses to this hypothetical person who's drinking water from no place else other than this well. And these are the doses that we find. So this is This is for that person. This is the dose in millirem per year. And as I said, the iodine 129 is the biggest. It doesn't peak until after, about a little bit after 1 million years. And the dose is 10 to the minus 2 millirem per year. Now the allowed dose in the United States is 15 millirem per year. So we put 10 millirem a year for historical reasons, but we're a factor of 1,000 below the limit that's allowed. So the safety factor is 1,000. That safety factor allows us to do many, many things. I should go quickly now because I don't have much time left. We do a sensitivity analysis in which we do 400 different simulations for 400 different rock configurations. These are all in our published papers. We assume there's an earthquake, a huge earthquake going right through it. And the amazing thing is, it makes very little difference. This is without the earthquake, this is with the earthquake. We understand this now, having done the simulation. The material goes up the earthquake fault, but it's 1.5 kilometers down. So as it's coming up, it begins to diffuse off to the sides. That gives an exponential decay loss. And so we're very insensitive to that. This is the borehole. If the borehole is poorly sealed, maybe after 1,000 years, you put cement in there, but it's crumbled into sand, it's still safe. And for the same reason, even though it'll go up this hole, it tends to diffuse off and advect off into the side rock. So we have in one of our articles solely about the sealing of the rock. We discussed the earthquakes. This is what happens if the engineered barrier, whatever you want your engineered barrier to be, let's assume it fails immediately. And part of the engineered barrier are the pellets that hold the nuclear waste. Let's assume they just disappear. What happens? Very little. The radiation gets up a little bit sooner, doesn't get any higher, and the reason is most of the safety comes from the rock. So these are the papers again. Here's another configuration. This is the surface here. This is an underground facility, and here we have an array of our. It makes some sense for large pieces that don't fit in boreholes to be able to put it in a mined repository. We call this a mined repository plus because you put the high-level waste in the holes. And this is a modular design, pictures of the canisters. We've developed a canister to go down the hole. We have some discussion of earthquakes in Korea. We certainly have looked at that. The earthquake that was likely caused by the EGS facility was caused by pumping fluids at high pressure underground. We don't do that. I just want to emphasize that in our directional drilling, it's not like the geothermal where you put high pressure water underground. It's quite different. More about famous earthquakes, but the accelerations are just not very high. The waste is safer underground than it is above ground. We've done vertical boreholes in crystalline basement rock. We do the best simulation. In addition to advection and diffusion, we include in cracked rocks. So there's transport in the cracked rocks. Don't have time to go through all this, but we find a similar thing. Here's the vertical hole, and we find that, once again, for all different scenarios, including early failure scenarios, we are a factor of 100 to 1,000 safe. So I'm almost finished. These are some of the simulations. Here's the worst scenario we can come up with. We have a horizontal repository, and we have two earthquakes, one of which provides high pressure water from the bottom that doesn't reach the surface, the other which goes to the surface. So this pushes water along the repository and up out. And even then, we get safety. So going up, there's safety in depth. Again, these are all in our. The heating is not a serious problem because they're quite close to each other. As I said, we can retrieve. That means if your community doesn't want disposal, you can use storage this way. And after about 12 years, we calculate it is less expensive than putting it into above ground storage. There's very little that we do that has not already been demonstrated. And the reason is we're bringing two technologies together. Very highly developed drilling technology, very highly developed nuclear handling technology. And we estimate our cost is much lower than a mine repository. There are several reasons for that. No humans underground, much less rock is removed. The drilling technology is very well established because of all the tracking, but we don't track. Modular, so you can leave it where it is. We can do it on a faster time scale. If you have one reactor that has some fuel in it, you don't have to build a big mine repository. You can just put it underground, most likely where that reactor is now. So that's it. And sorry if I ran over a little bit, but that's what we're doing. I believe that 20 years from now, this will be the standard method for the disposal of nuclear waste. Anyway, my slides are available. All of these slides are available. I have updated slides I will send in tomorrow to get the most up-to-date slides. I made some minor changes in the ones I sent in previously. But please feel free to call me, to email me, look at our website, watch the two videos, and thank you very much for your attention.
Thank you so much for your Thank you so much for your presentations. Now I would like to open the floor for your questions. I have questions. Before your presentation, the chairperson of Korean Nuclear Society said to us, cost is very important. So, in the sense, I'd like to know how much can the deep well disposal reduce compared to deep geological disposal?
Okay. So, I didn't say it, because if I gave you the number, you wouldn't believe it. But let me just say it's much less than 1/2 the price. And I think the real answer is much less than 1/2. The real answer is look at this list. And this list will convince you that the price is really much lower. We remove less rock. We use it using a standard drilling technique. There's no humans underground. It's all remotely handled. You don't have to build a big repository and then start putting things in. So the number we get is something like 1/4 of the cost of mine repositories, but I believe it can be less.
Thank you so much.
Some of the costs are fixed. I mean, you have to transport it there to the site. We have much less transportation costs. You have to put it in the canisters. Well, so do you, but those are costs for both of us. You have to make the canisters. Those are costs for both of us. Our canisters do not have to be very special canisters. So, and just every cost category is much lower. And that's why I think you should be convinced that the cost is going to be much lower. I can't convince you unless I show you the detailed work that we did with Bechtel to calculate these costs. But that's not my field. I'm a scientist.
Okay, thank you so much. I'm going to contact you and say goodbye today. Okay. Thank you so much. Bye.
Oh, you're welcome.
Bye.
Goodbye.